You know that feeling when you type a question into an AI, hit enter, and then you just sort of sit there?
Oh yeah, staring at the screen.
Exactly. You watch that little cursor blink or the loading animation spin, and you wait.
It is a very specific, very modern kind of agony, honestly.
Right. Because you know the math is happening at the speed of light, but you are still sitting there for what feels like an eternity.
We've built these miraculous machines, yet we still find ourselves tapping our desks, waiting for them to speak.
It's so frustrating. You're sitting there thinking, come on, I just asked for a recipe for banana bread. I didn't ask you to solve cold fusion.
Right.
Why is this taking so long? And that shared universal frustration is, well, it's exactly where we are starting today.
It's a great starting point.
We've got our hands on a deep, highly technical piece from tech-reader.blog by Aaron Rose.
Great article.
It really is. It's titled The Secret Life of Azure, the Inference Optimizer. And it opens with a character I think we can all relate to right now. His name is Timothy.
Timothy is a system operator, and when we meet him in the article, he is quite literally sitting in front of a terminal, tapping a stopwatch in sheer frustration.
Because it's taking the system a full 5 seconds just to answer an incredibly basic question, he literally just asked, is the archive open?
5 seconds.
Yeah. And in the world of enterprise architecture, 5 seconds is a lifetime. I mean, you can't build real-time applications if every interaction has a 5-second latency penalty.
You really can't. It breaks the whole illusion of interactivity.
So our mission for this deep dive is to figure out exactly how modern AI systems are solving this latency problem.
Right, looking under the hood.
Exactly. We're looking under the hood at the inference architecture to see how these models are getting dramatically faster and more efficient without, sacrificing their intelligence.
Okay, let's unpack this.
To understand the solution, we first have to diagnose why Timothy is waiting those 5 agonizing seconds.
Right, the root cause. Yeah. The author introduces a system architect named Margaret who identifies Timothy's bottleneck, and she calls it the density trap.
The density trap. I like that. But let's break down what that actually means mechanically. We know that these large language models are massive neural networks, so are we just talking about the sheer size of the files?
Well, no, it goes much deeper than just file size. It's about how the transformer architecture actually utilizes hardware.
Okay.
The density trap happens because the system is treating every single user prompt as a high reasoning crisis.
Ah, I see.
Whether you ask it to summarize a 100-page legal contract or, like Timothy, just ask if the archive is open, the system is spinning up the exact same massive billion-parameter model to formulate a response.
Meaning, for every single word or token that the model generates, it has to load those hundreds of billions of parameters from the GPU's memory into its compute cores.
That is the core of the issue, yes. It's a memory bandwidth bottleneck.
Right.
The compute cores on modern GPUs are incredibly fast, but they spend most of their time sitting idle, just waiting for the massive weight matrices to be transferred from the VRAM.
So the brain is fast, but it takes too long to get the information to the brain.
Exactly. Margaret uses a visual on her whiteboard for this, which I thought was great. She draws a heavy-lift cargo plane.
Oh, yeah. The cargo plane.
Timothy is essentially firing up the jet engines of a massive cargo plane, coordinating air traffic control, burning tons of jet fuel.
Just to deliver a single postcard.
Exactly.
It's like hiring a team of PhD theoretical physicists just to calculate the tip on your lunch bill.
That is a perfect analogy.
Right. Like, sure, they'll get it right, but it's a massive waste of time, energy, and money. You don't need a physicist for that. You just need someone to move the decimal point.
And we really have to remember the scale here. This sledgehammer to crack a nut approach isn't just frustratingly slow for the user tapping a stopwatch.
It's expensive.
It is astronomically expensive for the provider. Running those giant models requires massive clusters of GPUs drawing immense amounts of power.
Just burning cash.
Literally.
Yeah.
It costs a small fortune in compute just to say, yes, the archive is open.
So if the problem is VRAM bandwidth and compute waste, the logical fix is to just stop using the massive models for everything.
It sounds simple.
It sounds simple, but you still need the cargo plane sometimes, right?
Yeah.
You still need the PhD physicist for the hard stuff. So how do you build a system that knows when to use the genius and when to use the calculator?
That leads directly to the first major architectural shift they talk about, which is tiered inference.
Okay.
Instead of one monolithic model, the system uses an ensemble. And the front line of that ensemble is a small language model, or SLM.
Like a filter.
Exactly. In this specific Azure deployment, they use a model called a Scout.
Right. The article mentions they are using Phi-3 for the Scout role. And because Phi-3 is so much smaller, it easily fits entirely within the faster memory of the GPU. So it avoids that memory bandwidth bottleneck entirely.
It flies.
Yeah.
I mean, it is the sleek jet from Margaret's drawing, designed to run in milliseconds, not seconds.
Wow.
And what the telemetry showed is that this little Scout model can actually handle about 80% of the daily prompts.
80%?
Yeah, the basic Q&A, formatting text, simple classifications, 80% of the traffic never even needs to touch the heavy lift models.
Okay, I buy that. Send the easy questions to the fast, small model. But, that introduces a massive risk.
How so?
Well, how does the small model know its own limits? Anyone who works with LLMs knows they are notoriously overconfident.
Oh, absolutely.
If I ask the Scout a highly complex coding question, isn't it just going to confidently hallucinate a terrible answer at lightning speed?
What's fascinating here is how the architecture prevents that exact scenario. The Scout model is equipped with a strict confidence threshold.
Okay.
It doesn't just generate text, it analyzes its own probability distributions.
You're talking about the log probs, right? The probability of the next token.
Yes, exactly. When a prompt comes in, the Scout calculates the likelihood that its predicted tokens are correct.
So it's double-checking itself.
Right. If the top choice token has a 99% probability, the model is highly confident.
Makes sense.
But if the probability distribution is flat, meaning it sees 5 different potential words that all have like a roughly 10% chance of being right, it knows it's effectively guessing.
It detects its own uncertainty. That's really cool.
It is. And the threshold is rigidly set at 95%. If the Scout is 95% sure it has the correct answer based on those internal metrics, it fires that answer off instantly to the user.
And what if it's only, say, 80% confident?
It steps back immediately. It refuses to guess.
Oh, wow.
Instead, it seamlessly escalates that specific query up to the heavy lift, high parameter model.
It's essentially an emergency room triage system.
That's a great way to put it.
Yeah, the Scout is the nurse at the front door saying, okay, scraped knee, I can patch that right now in 2 seconds. Oh, a complex fracture. I'm not touching that. Let me page the specialist.
That is the essence of tiered inference. It routes tasks dynamically based on statistical confidence, keeping the massive models reserved only for the prompts that truly require deep reasoning.
Okay, I see the elegance there. You've solved 80% of the problem. Timothy is getting instant answers for all the daily chatter.
Right.
But I see a massive flaw here.
Let's hear it.
What about that remaining 20%? Triage is great for keeping the waiting room clear, but it doesn't actually make the specialist any faster. If my prompt is complex and falls into that 20%, the Scout steps back, and I am still caught in the density trap. I am still waiting 5 seconds for the heavy lifter to generate a response token by token. You haven't sped up the big model, you've just diverted traffic.
That is the exact friction point Timothy brings up to Margaret. And her solution to that 20% bottleneck introduces perhaps the most ingenious piece of engineering in the entire article.
Okay, I'm ready.
It's called speculative decoding.
Speculative decoding. This was the densest part of the piece, so let's walk through the mechanics carefully.
Sure. So when a complex task is escalated, the small model, the Scout, doesn't just go to sleep.
It's still working.
It stays active, but its role shifts. Instead of trying to answer the complex prompt perfectly, it starts speculating. It drafts a sequence of, say, 5 to 10 tokens at lightning speed.
It's sketching out a rough draft of the answer.
Yes.
Yeah.
And then the giant model, the heavy lifter, steps into a new role. It acts as the validator.
Okay.
It takes the chunk of text the small model just drafted, and it evaluates the entire sequence in a single forward pass.
Okay, wait, I have to stop you because I'm going to push back on this just like I did when I read it.
Go ahead.
If the big model still has to read and check the small model's draft, how does that actually save any compute time? A massive model still has to process those tokens. Isn't it faster for the big model to just write the answer from scratch, rather than having to proofread the little model's homework?
It's a completely intuitive pushback, but it requires us to look at how GPUs actually process data.
All right, hit me.
Generating text from scratch is an autoregressive process.
Yeah.
It is strictly sequential.
One word at a time.
Exactly. The model has to calculate token 1, output it, feed it back into itself, calculate token 2, feed it back, and so on.
Right. It's locked into moving one step at a time, which means the GPU's massive parallel processing power is mostly sitting idle while it waits for memory.
But reading and validating text that already exists, that can be done in parallel.
Ah.
The giant model can take a string of 5 drafted tokens, load its massive weight matrices into the compute cores once, and validate all 5 tokens simultaneously across its parallel architecture.
Okay, I'm tracking now.
Margaret uses an analogy of a lightning-fast typist being supervised by a genius editor.
I like the typist and editor concept, but I still have a logistical question here.
Sure.
Reading is parallel, writing is sequential, I get that. But the small model still has to write the draft sequentially, right?
Yes, it does.
So if the small model is doing all this writing, aren't we just bottlenecked by the small model's typing speed?
That brings us back to the memory bandwidth issue we discussed earlier. The big model is painfully slow at writing sequentially because it has to move billions of parameters across the GPU memory bus for every single word.
Right, the cargo plane.
Exactly. The small model, though, is so lightweight that its parameters fit entirely in the ultra-fast on-chip SRAM. It doesn't face that memory bottleneck.
Wow.
The small model can auto-regressively generate 5 tokens faster than the big model can generate a single one.
Oh, the light bulb just went on.
It's wild, right?
The compute cores on the big model are normally just waiting around for data to arrive from memory. So speculative decoding takes advantage of that idle time. It says, hey, while you're waiting, here are 5 words the little guy already wrote. Just run the math on these all at once.
The math backs that up beautifully. If the genius editor, the giant model, evaluates those 5 tokens in parallel and finds that they mathematically match what it would have generated itself, it accepts them all instantly.
That's incredible.
You just got 5 tokens of output for the time cost of 1.
But wait, what if the fast typist makes a mistake? What if the small model drafts 5 words, but the big model says, wait, word number 4 is wrong? Does the whole system just crash?
No, the architecture is incredibly fault-tolerant. If the giant model rejects token number 4, it simply accepts tokens 1, 2, and 3.
Okay.
It then generates the correct token number 4 itself, tosses at token 5, and tells the small model to start drafting a new sequence, starting from that correction.
So the user still gets the absolute maximum intelligence of the heavy lift model, but because so much of the sequence is being rubber-stamped in parallel, the overall output speed just skyrockets.
The benchmark data in the article shows that for complex queries, speculative decoding allows the logic to stream up to 3 times faster than traditional autoregressive generation.
3 times faster for the hardest queries.
Yeah.
That is a staggering optimization. You're getting the deep intelligence of the giant, but delivered with the speed of the scout.
It is brilliant, but Margaret's architecture has one final layer. Because there's one more major inefficiency to solve.
Okay, let's see. We've optimized the simple tasks with the triage scouts. We've optimized the complex tasks with speculative decoding.
Right.
But there's a third category. What if a user asks a question the system has already spent compute power answering before? Like, do we really need to do all of this elaborate drafting and validating all over again?
This brings us to the final concept Margaret maps out for Timothy, which is semantic KV caching.
Okay, here's where it gets really interesting, but I have a bone to pick with the source article first.
Oh.
Yeah, Margaret draws a lightning bolt hitting a storage box to explain this to Timothy. I hated that analogy. It's a cliche that explains absolutely nothing about how the process actually works under the hood.
I agree. The visual is a bit reductive. Caching itself is an ancient concept in computing. You know, your web browser caches images so it doesn't download them twice.
Sure.
But traditional caching relies on exact matches. If you search an FAQ database, you need to type the exact keywords. Semantic KV caching is entirely different. It doesn't just save the text, it caches the mathematical meaning.
Okay, let's define the terms for everyone. KV stands for key value. What is the key and what is the value in this context?
When you submit a prompt, the model doesn't read English. It converts your words into high-dimensional vectors.
Arrays of numbers.
Exactly. Arrays of numbers that capture the contextual meaning of the prompt. In the attention mechanism of a transformer, these representations are the keys. The values are the actual computed mathematical states that generate the response.
So the system is storing these abstract mathematical keys and values in a massive vector database.
Yes. Now imagine user A asks, "Is the archive open today?" The system computes the vector key, processes the answer, and stores that key value pair in the cache.
Okay.
An hour later, user B asks, "Can I access the library records right now?"
The words are completely different. A traditional keyword cache would see 0 overlap and force the model to compute the answer all over from scratch.
But in a semantic cache, The system looks at the mathematical vector for user B's prompt, and it measures the distance between that new vector and all the stored keys in the database.
The semantic distance.
Right. The math reveals that the vector for is the archive open today and can I access the library records right now point to the exact same neighborhood in that high-dimensional space.
Because they mean the same thing.
Exactly. The system's governor detects that semantic proximity. It realizes, hey, I have already solved this exact mathematical equation.
I think a much better analogy than a lightning bolt is a really experienced librarian.
Oh, like that.
Yeah. The librarian doesn't memorize the exact titles of the millions of books. They memorize the conceptual coordinates of the library. So whether a student comes in and says, I need data on the respiratory system or where are the books about lungs, the librarian isn't looking for matching words.
They know exactly where to go.
Right. They are mapping both entirely different sentences to the exact same conceptual coordinate on the third floor.
That is a far more accurate representation of how vector similarity works. And because the meaning is the same, the system bypasses the generation process almost entirely. It just fetches the pre-computed value from the cache.
There is a quote from Margaret here that I think is the thesis of the entire deep dive. She says, we aren't just thinking faster, we're thinking less.
It's a profound paradigm shift. For the last few years, the entire industry assumed that advancing AI simply meant brute force, larger models, vastly more parameters, more data, more power.
Just throw more hardware at it.
Right. But what Aaron Rose illustrates with this look at the inference optimizer is that brute force doesn't scale. The true frontier of AI engineering isn't just intelligence, it's elegance. It's about preserving resources.
Which brings the narrative full circle perfectly. At the end of the piece, we are back at the terminal with Timothy. But the dynamic has completely changed.
He's not tapping the stopwatch anymore.
No. He's watching the system logs. A simple status update comes in, and the Phi-3 Scout handles it instantly via triage.
Milliseconds.
Then a massive, complex migration query hits the server. Speculative decoding engages, the Scout drafts, the heavy lifter validates in parallel, and the logic streams across his screen 3 times faster.
Incredible to watch, I'm sure.
And then a redundant query hits, and the semantic cache resolves it in 0.01 seconds.
And where's the stopwatch?
The stopwatch stays in his pocket. Timothy watches the terminal and realizes it's not just smart anymore, it's instantaneous.
Margaret summarizes the driving philosophy of modern architecture in her final exchange with him. She tells Timothy, in a world of infinite data, the most valuable resource isn't intelligence, it's time.
The most valuable resource isn't intelligence, it's time. Wow. So what does this all mean for you listening right now? Well, the next time you type a prompt into an AI and you get a brilliantly reasoned, multi-paragraph response practically before you've even lifted your finger off the return key.
Which still feels like magic.
It does. I want you to picture that invisible, highly orchestrated team working in milliseconds behind your screen. Picture the Scout model running ahead to check the easy stuff. Picture the lightning-fast typist drafting sequences for the Genius editor to validate in parallel.
And the cache.
Right, and picture that vast vector database of pre-computed thoughts, mapping the semantic coordinates of your question so the machine doesn't have to think twice. It really changes how you look at that blinking cursor.
It absolutely recontextualizes the technology. And, it actually raises an incredibly important question, something for you to mull over after we wrap up today.
Oh, I like where this is going.
Well, think about it. If artificial intelligence is becoming hyper-efficient by caching the meaning of its computations, literally finding ways to map new inputs to old coordinates, to avoid thinking the same thing twice, at what point does human learning start to mimic this?
Oh, wow.
In our own daily routines, at our jobs, or, even in our personal relationships, are we actively thinking through our problems each time they arise? Or are we just relying on our own biological semantic cache?
That's deep.
When someone asks you a question, are you truly doing the cognitive work to generate a novel response, or are you just pulling a pre-computed reaction from the cache to save your own mental bandwidth? Are we thinking, or are we just matching patterns?
That is a wildly provocative thought to leave off on. Are we actually thinking, or just pulling from our own biological cache to save time? Incredible. Well, keep that in mind the next time you answer a question instantly. Until next time.